to the meeting. And I'm from University of Colorado, so I began the talk. And so we're talking about cluster and agglomerates, which if we look at non-cohesive particles, which is basically group B or group D particles, these two terms can sometimes be used interchangeably, and it all refers to a higher concentration, a local higher concentration. But if you look at cohesive particles like group A or group C particles, and it's worthwhile to treat those two terms differently. So clusters we usually refer to as of hydrodynamic origin, such as it can result from inelastic particles, friction, or the gas solids drag forces. And it is characterized by collision, so that the particles in the clusters can bouncing back and forth and without forming enduring contacts. So different from cluster, if you look at agglomerates, so it can just like it can form from van der Waals forces or liquid bridge, and different from clusters, that is particles bouncing back and forth. It can form the agglomerates, the particles in agglomerates form enduring contacts. So as here showing an example in experiments, we are isolating a agglomerates in the system. Since it is likely that because of the different behavior of particles inside cluster and agglomerates, it can affect heat transfer and chemical reaction rates depending on whether particle is forming enduring contacts. So it's worthwhile to separate these two and analyze the interactions between clusters and agglomerates. So we can first look at the granular system, so here, and then move on to the gas-solid system we are focusing on in this study. So in the granular system, so here for showing an example is the simple shear flow, where we apply at least adverse boundary conditions on the top and bottom of the system, and the system the gravity is absent in the system. So as the system evolves, we see these streamers of particles, a local higher concentration of particles characterized as clusters. So if we add some cohesion to the system and increase the solid concentration, we are expecting to see a larger, more clustering due to the increased collision frequency between particles. So, if we look at a cohesive system here, in addition to increased cluster, they also form a big agglomerate showing here. So that somehow indicates that in the granular system without gravity and in the without fluid, where the fluid effect is negligible, the clustering is enhancing agglomeration, which makes sense because when we have clustering, we have a reduced impact velocity, which is defined as the relative velocity between particles before they collide. This impact velocity reduces, the particles will turn to agglomerate more easily. So that in granular system, we see this clustering enhance agglomeration. So this work will just focus on the gas-solid flow, and which is different from the granular system because first is the gravity-driven system, and we have a gravity for the both phases, and we have a non-zero gas-solid relative velocity in the system as well. So we are working, we'll use CFD-DEM for this study, and here's just a governing equation here. And CFD-DEM is just corresponding to the Eulerian-Lagrangian framework of the modeling. So we just use conventional CFD to model the system, and we track the particle trajectories via Newton's equations of motion. And the gas phase is solved on a grid that is 2 particles diameters large, and we couple the gas and solid phase via a solid concentration and a slip velocity dependent drag law. And here we summarize the simulation conditions here, and we have a gas phase that mimic the properties of air, and we have a particle phase here that is typical of the group A particles. And we are varying the system's domain to have a variation of clustering, which we have found in non-cohesive particles. And we are adding a cohesion using the simplified cohesion model, which we are just adding a cohesion as during when particles are in physical contact. So when the overlap in DEM is larger than 0, we apply a constant cohesion to the particles. And this cohesion model is simple, but we have found recently that it can be a valid surrogate of more cohesive models as we match the cohesive energy, which is the area under the curve for this for this function of cohesion force as a function of separation distance. So in the system, so here is just a system shown here, and we are using a 3D simulation with fully periodic in each direction, and we maintain a constant mean gas flux in the vertical direction. So we start with a system that is when particle is randomly placed, and we start apply the gas phase in the vertical direction. And as the time evolves, we see that we have the streamers of clusters forming, and also the system is, we are getting some non-homogeneities in the system. And here on the right, we are showing this, the mean vertical velocities of particles as a function of time as it evolves. So for these 3 different bed widths, we are seeing that as the steady state is reached before 1 second, so that we can use the data here for the steady state to extract the steady state value that we analyze later. So here we can first do a visualization of the clustering. So we can just look at a slice view of the inside the bed, and we see that here we have some streamers, and we have locations where we have more particles, and other locations that there are fewer particles than the surrounding, so characterized by the clustering behavior. And also in the simulations in DEM, it is straightforward to record the contact durations of particle contacts, so that allow us to detect agglomerates, which we define as when we have a contact duration larger than the contact duration for typical non-agglomerating collisions for non-cohesive particles. If the contact duration is longer than that, we will define as a pair of collisions to be in agglomerates. And this agglomerate will only break upon a collision of another particle or agglomerate. So here we're showing an enlarged view of this region and only showing the isolated agglomerates here. And we're showing that under the current cohesion, this is a laterally cohesive system. I forgot to mention earlier that we are only seeing smaller agglomerates, so characterized with singlets and probably characterized by doublets and probably 1 triplets here. It's just a 3-particle agglomerate. Doublet is just 2-particle agglomerates. So to quantify the clustering agglomeration, so the last slide we showed the visualization. Now we quantify the clustering agglomeration. So first we introduce this heterogeneity index, which is basically the measure of how the distribution of local solid concentration is deviating from the Poisson distribution, which is corresponding to the random distribution of particle positions at the initial condition. So we can plot that as a function of time, and it is reaching steady state. And this heterogeneity index will characterize the levels of both clusters and agglomerates, which can cause enhanced local concentration. And also we define this agglomerate fraction, which will help us isolate the agglomerate effect, which is defined as the number of particles in agglomerates over the total number of particles in the system. And this parameter is measuring the level of agglomeration only, so because we are only looking at the detected agglomerates. So as we see that we analyzed earlier that after 1 second the system reached steady state. So we use the steady state value and analyze and study its response to increasing system size. So as we're showing here that with increasing system size, which is showing as the bed width here, we have increase of the overall level of heterogeneity, which is characterized by the heterogeneity index D here. And we have a decreasing level of agglomeration characterized by the agglomerate fraction. So that, as we discussed earlier, that this D include two contributions. One is from agglomeration and one is from clustering. So we have D increasing and this agglomeration decrease. That indicates we have an increased level of clustering. So that indicates we have this opposite behavior of clustering and agglomeration identified in the gas-solid flow, which is somewhat surprising and is different from the granular system we have seen. Agglomeration is enhanced by increased level of clustering. So we'd like to analyze this observation. And first, we can get some clues from particle velocity statistics. So here we have summarized the velocity distributions of particles as three different bed size. And we are compared. So this is the distribution of fluctuating particle velocities in these three directions. The y is the vertical direction, is in the direction of the mean flow. And we found that compared with this Gaussian distribution, this distributions extracted from the simulations, which are represented by symbols, is deviating from this Gaussian distribution. And we also have a skewness of the distribution for the vertical direction in the mean flow direction. And this is consistent with the recent experiments for group A particles. And if you look at the width of the distribution and compare the different bed widths, we see that the distribution is getting wider as we increase the bed width. So that means the variance of the velocity, the fluctuating velocity, is increasing as we increase the bed width. So with the increasing variance of the velocity distributions, we are expecting the impact velocity distribution to switch to move to higher values. The impact velocity, as we just defined, is the relative velocity, relative normal velocity right before a pair of colliding particles. So as we see that when we have at higher bed width, we're seeing the velocity distribution is moving towards larger values of impact velocity. So when we have larger impact velocity, the particles will tend to separate from each other after collision, so that we'll expect to see a deagglomeration. So this gives us a direct understanding why we have a deagglomeration as we increase the domain size. So we did some quick quantitative analysis on deagglomeration just to give further evidence of this the decreased agglomeration as we increase the variance of velocity distribution. So here at steady state, if we just massage the population balance equation, because here, as we saw earlier, we only have doublets in the system. If we assume that, we'll reduce the population balance equation, and we have in the steady state, we'll have the this equation that governs the steady state, which we have the collision frequency of single collisions, and times the probability of agglomerating collisions, which is also called success factors. And that is equal to the frequency of doublet collisions, and which leads, and this is the success factor of breakage, which is the probability of a doublet collision that leads to breakage of the system. So this is a number density that is can be related to the agglomerate fraction. So combining these equations, we have a simple equation that helps us relate the agglomerate fraction. And first, we will highlight here that S12 and S11 is just the collision cross-section area. So for the X11 is the collision cross-section area for single collisions, which is just the local eye of points that the particle will collide with another particle. So it's the area here. So for the singlet, it's simple because it's just pi dp squared, which dp here is the particle diameter. And for singlet doublet collisions, it is dependent on the orientation of the doublets here. So here, for example, as we isolate one doublet in the system, it will have a particular orientation that can be characterized by this orientation angle phi. And also, so this collision, so the collision cross-section area is showing here is just given by this shaded area here. So this collision crossing area will be dependent on its orientation angle. So guided by the simulations, we can extract the distributions of the orientation angle in the system, and then we can have this expectation value of the collision cross-section area that is used in this equation to predict the A. So next we'll evaluate the success factors. The success factors, as we discussed earlier, is also simple, that it's just the probability of agglomeration and breakage, the collision that leads to agglomeration and breakage. For agglomeration, we all know that when we have a boundary collision, the two particles will agglomerate as long as their impact velocity is smaller than a particular critical impact velocity. So here defined as liquid, and this if we integrate this impact velocity distribution, we will get the success factor of agglomeration. And similarly, we can define breakage, the critical breakage velocity, and integrate the impact velocity distribution to get success factor of breakage. But as we'll see later, this can be a little bit more complicated. But so here is so how to determine the liquid here, and here we just show using our dimensional analysis. We show in our previous work that we can just do a Buckingham pi analysis, and then determine a general formula for this liquid here, and which is a relation, which is dependent on the cohesion force, the Young's modulus, the Poisson ratio, particle size, and particle density. And here is a numerically determined constant C, and that is we got it numerically, but it's in general can be applied to any system with any materials with if we provided that we know all these parameters. And for this system, we determine that liquid the critical velocity agglomeration to be 0.6 centimeter per second. And now we move on to the critical breakage velocity, which is much more complicated because it now includes three-body collision. And here we are showing here as we increase the impact velocity, there's just evolution of different types of collision outcomes. So when we have smaller impact velocity, we are expecting to see that the three particles will form a triplet after collision. And as we increase the impact velocity, they can have a bounce where they just the singlet just separate from the doublet after the collision. And they also can have a transfer where the original doublet breaks after the collision, but the singlet is re-agglomerated with one of the singlet and to form another doublet. And also, and lastly, we have this breakage event when we have very high impact velocity. So that way, the collision will result in three singlets after collision. So we are interested in this regime from transitioning from agglomeration, bounce, or transfer to breakage. But we see that this critical velocity is highly dependent on the pre-collisional configurations, like the relative location of the singlets to the doublet, as well as the velocity vector, the angle of the velocity. So in this work, for simplicity, we just also did an expectation value by summarizing the data we collected in the new DEM simulations. We just take a expected value and use that in the theory we just developed. So by using that, the collision cross-section area as well as the success factor we just described, we see that we can have a theoretical prediction of the agglomerate fraction, that we have better agreement when we have, especially at larger system sizes. And not so good agreement is found when we have smaller system sizes. And we found that in addition to the errors associated with collisional velocities, we also see that when we have smaller system, we have larger agglomerates forming. So here is just the mean agglomerate size as a function of system domain size. We see that when we have smaller system domain, we'll have we'll have increasing number of larger particles beyond doublets, which is not modeled in the current theory. So that can be a future modeling effort in terms of using more generalized population balance. So now why we have this larger agglomerate, we have larger variance of velocity when we have a larger domain size. I think that can be also attributed to the increased level cluster. So as we found recently in this direct numerical simulations, and when we have a cluster forming, they tend to fall down, and this falling of clusters will consequently collide with smaller particles, with individual particles or smaller clusters that can lead to additional collision between clusters, between particles. So that can cause an added source of collisional energy that is causing an increased variance of velocity distribution, as well as the increased collisional impact velocities. That can help us understand physically why we have a decreased level of agglomeration as we increase the domain size. So here is evidence showing here that the evidence showing here that as we increase domain size, here we compute the average velocities as a function of domain size. We see that as we increase domain size, we have more downflow. That is evidenced by the decreasing average velocity showing here. And also we can see here that when we have a larger domain size, we have more regions corresponding to downflow here. And that is also corresponding to the regions where we have a cluster of particles, like streamers here. And we demonstrate the robustness of this regime in system with increasing cohesion here. So here we are increasing cohesion and showing by the bond number. The bond number is the cohesion force over gravity. So as we're showing here, when we have increased bond number, we'll have increased, instead of showing that the agglomerate fraction will tend to 1, so that all the particles form agglomerate, will form a big agglomerate in granular system. We are showing that this level of agglomeration is leveling off instead of going monotonically to 1. And so I think this can be also associated with the increasing level of clustering as shown by the increased level of heterogeneity here. So here we demonstrate qualitatively that this regime can be robust in system of increasing cohesion. So here's just a quick summary, and we found that there's the opposite behavioral cluster and agglomeration with increasing domain size in dilute gas solid flows. And we analyzed the particle velocity distributions to help us understand the observation and propose a simple relation to determine the agglomerate fraction. And we found the mechanism is robust in system with increasing cohesion. I think this study can be used for when we model the cohesive particles. We need to separate modeling of agglomerates as well as cluster, which can lead to different phenomenon because they have different phenomena with increasing domain size. Thank you for your attention.
I see about 5